Hey YouTube, welcome back to my channel. Today we're gonna solve a hard level question. Although it's hard level, it's not that challenging. If you struggled with merging case sorted lists, this video is for you. By the end of the video, you will understand how to use the priority queue or the minimum heap to solve this problem better than brute force. Alright, so let's dive in. We're given an array of k linked lists. Each linked list is sorted in ascending order. We need to merge all the linked lists into one sorted linked list and return it. You can simply just, extract all the elements in these k arrays and put them into an entire array and sorted that array to get the answer. Like we put 1, 4, 5, 1, 3, 4, and 2, 6 to a single list, and then perform like a merge sort or quick sort to this linked list. And basically we will have a n log n time complexity. N is the number of the elements in all linked lists. So this solution is not that efficient. We can do better with using the priority queue or the minimum heap to reduce it to on log k. So k is the number of the lists. So if the k is much smaller than n, it will be much faster than the brute force solution. Okay, let's see how we're going to do this. So the heap helps us always extract the smallest element efficiently. Instead of sorting everything at once, we only store the smallest elements from each list in a minimum heap. So basically, in brute force, we kind of ignore the information that all these lists are sorted. So we can use this information in minimum heap to help us solve this more efficiently. We will keep k elements at a time in the minimum heap. So first, we will put the first node of each list into the heap. So basically, we will perform a minimum heap. So the root node will be the smallest comparing with its children. So the first element is 1, 1, 2, right? So 1, 1, 2. The root node is smaller or equal to its children. We will pop out the smallest element, which is this one, to the result list. After popping out the smallest element, we will check if its next element is empty. If not, we will append it into the heap. Say this element is according to the first list, so the next value will be 4. As we popped it out, we will cross it out. And we will append this 4 into the heap. Since we have popped this 1 out, we will reheapify this minimum heap. So we will have 1 and 2. And since we append the 4, we will append it here. So basically, we will repeat the process until the whole heap is empty. So then we will pop out this one to the result list. And then we will cross this one out and see the next node of this one. It's 3, right? So we will reheapify this entire heap to this. Then 2 is the smallest, and we will pop it out and cross it out and append the next node of 2, which is 6. And we'll have this heap, and we will pop out 3, cross it out, and see the next node is 4. So we will have 4, 6, and 4. Then we'll pop this out. We can either pop this 4 or this 4. So in this time, we will pop this one. So then we have the 4, 6, and 5. And we'll pop this 4. Since the next node is empty, basically we append no element into the heap further. So in this heap, we just have these 2 elements. And then we'll pop this 5 out. So the next node of the 5 is also null. So we will not append any elements into the heap again. Then we just have one node, which is 6, and we'll pop it out. And basically, we popped out every element in the initial lists. So we can rearrange our result and to see that the first is 1, right? So first is 1, and second is 1, third is 2, fourth is 3, fifth is 4, sixth is 4, seventh is 5, and eighth is 6. So basically we have this result list. The output is what we expected. Then we can solve this problem. Because every time we insert or push a new element into the heap, the time complexity will be log k. Because every time we, maintain a minimum heap with k elements, right? Every time we insert a new element, the time complexity will be log k. And basically we traverse all the elements from the node n. So it will be n times log k. For popped out, because we every time popped the smallest element, so the pop out will cost like just 0.1 time complexity in constant time. All right, so let's see how we're gonna code it up. All right, so let's code it up. So in the second example, we see that if the list is empty, we need to output none, right? So for this add case, we will write it first. If not list, we will return none. And as we said in the previous part, first thing we need to do is push the first node of each list into the heap. So first we will have a minimum heap, which is just a list. Then we will use a for loop to push the first node of each list into this minimum heap. So basically in Python, we will use the heap queue to implement the minimum heap. First argument here is the heap we want to operate on. And for second argument will be the value or the element or the object we want to append into the heap. So for this problem, we will first have a node.value to compare their value, who is larger, who is smaller, and the node itself. But there is an important thing to remember is that if the value is duplicate, how are we going to identify different node and different values? So we will append another identification, which is I, to distinguish the node that shares the same value. From the third example, if the first node of the list is empty, we will not append it into the minimum heap. We will just return none, right? So we will check if the node is empty. And then basically what are we going to do is to iteratively repeat the process to pop out the smallest element and append the next node of the current popped out node. So while the heap is not empty, we will repeat that. And we will pop out the smallest element from the minimum heap. And the value should be this zip. We will have 3 variables: value, identification, and the node. We'll use heap.heap heap. So by default, the pop is to pop out the smallest element of the minimum heap. So we just need one argument to assign which heap we want to pop out. Because in this problem, we are operate on the linked list. So if we want to return the correct value, we need to revise the next pointer for each node based on our sorted operation. So we will have a dummy head with 0 value, and then have a variable called cur. It's going to be dummy head in the initial step. Then basically the next pointer of the current dummy head will point to the popped out node, right? And then the current will be the current node. We need to check if the current node, the next value of the current node is empty. If not, we will push it into the heap. Heap queue.heap push the minimum heap, and the value will be the node.next.val, and the identification will be the same with the popped out node because they are in the same list, right? And the node will be node.next. And then after we visited every element in all the linked lists, we will return dummy head.next. Dummy is just empty, and next is the first node of the element that we popped out. So let's submit our code and to see whether it works. All right, so I hope you understand how this minimum heap works, and hope to see you in next video.